Excuse me. Cool. Okay, last one, and I go to sleep. Hopefully. 773 sliding puzzle. On a 2 by 3 board, there are 5 tiles represented by the integer 1 to 5, and an empty square represented by 0. A move consists of choosing 0 and 4 directionally adjacent numbers and swapping it. I said that in a weird tonation, but okay. A state of board is solved if and only if the board is 1, 2, 3, 4, 5, and 0. Given a puzzle board, return the least numbers of moves required so that the state of the board is solved. If it is impossible for the state of the board to be solved, return -1. So cool. Let me take a look at this one now. Okay. So it'll always be a 2 by 3 array, and there's a permutation of this. Okay, so right off the bat, I think there's 6 factorial number of combinations. What is 6 factorial? I'm just putting on my calculator. Hang on. Oh, 720. Okay. So right off the bat, it's only 720 states. So I think you could actually just brute force this. Yeah. What else do you need? I mean, you could brute force. Sorry, when I say brute force, I mean there's only 720 states, so you could do a breadth first search or depth first search if you will. But well, I don't know what the farthest state is, but I guess what I was gonna say is I don't know what the furthest state is. So sometimes with depth first search, you may run into what you call it. You run into stack overflow issues, which is not good. But if the most if there's 720 states, that means your max recursive depth is probably it's going to be 720 because that means you visit every state, right? And I think in this case, my first instinct is that there are impossible moves, but all of them will be siblings of I don't know if siblings is, but like they're all in a graph sense connected to this state. And my guess is that it's probably just like 2 things swapped, and there's no way to swap them back. And if that's my intuition, and what that means is that half the states, meaning 6 factorial is 720, but half of that 360 states are not accessible. So that means if you do a DFS, there'll be almost 360 states to go through. So like that's your max depth. I mean, and that's like a super weird worst case scenario. But I don't think we need to do that. I think whatchamacallit. Yeah, I mean, so I think like a breadth first search is probably the way I would do it. And I think that's it. I mean, I think there's just a lot of edge cases with like swap. What does it mean to swap? But I think this is probably fine. Yeah. So yeah, in breadth first, so there are two. As I mentioned, there are 2 ways to do it. But sorry, I'm just reading John's comment. Is like so. Yeah, exactly. So I mean, I think breadth first search um, will naturally give you the minimum number of states because if a state that you haven't seen before, it's like a shortest path problem, right? If you have a state that you haven't seen before, then you see it in the shortest way, like because all the weights, if you will, of the graph is 1 because you're 1 move away from the last move, right? So that's kind of and you can actually solve this. I don't know. I always forget how Leetcode does it, but you can actually solve this problem backwards because I think the graph is symmetric, right? Meaning it takes 1 move to get from here to the end state, but that also means that there's 1 move from the end state to get to this move. And knowing that, you can actually pre-compute all possible answers by pre-processing it from the end state and then kind of get it that way. And if your question is about how to get the minimum number of states for depth first search, so let me answer one question at a time. But if you're asking how do you do the minimum number of moves for depth first search, there's a variation of depth first search called DFS ID, which is depth first search with iterative deepening, I think, or deepening or deepening, I forget. But what that means is that you limit your branch of your DFS to that depth, and which another way of phrasing the question is, can I solve this problem with DFS on X move? No. Can I solve this problem with DFS in X+1 moves and so forth? And you can kind of iterate it that way. The complexity of solving that is not super great. So, and BFS is way trivial. So yeah, so John asked the question of how do you solve for an errata board position? So the answer is that if you try, so there are only, in this case, there are only 360 states, right? Or we assume that there are only 360 reasonable states in that case, right? But if you look at it in terms of graph theory, or like the shortest path type thing, right? Then like you're like, okay, from this state, I could get to these maybe 3 states or something like that. I have to look at the swap, but like I could get to these 3 or 4 states that are, 1 move away, right? And then you have like in the shortest path problem, you have a list of like states that you've already seen, and in that case, you'll be like, oh, I want to do this move, but I already seen it, so I'm not going to do it. I want to do this move, but I already seen it. And then in this case, when you have no more moves, then the entire graph, like you would have walked the entire graph. So I mean, I think if you, wow, you guys are really ahead of me on this one. I actually was going to get to it as like kind of optimizations that we could do, and I haven't even started coding yet. I've just been rambling on a lot. but yeah, so I think, to be honest, I mean, some of it's intuition, and I haven't solved this particular one, but I think I've seen similar ones where, these are like kind of similar to in math. There's and this is very high power math, so that's why I hesitate to kind of jump into it a little bit. But in math, about group theory, there's some part of it that deals with permutations and permutation theory, and then you have these, and you could describe each move as kind of as a swap. I forget what it's called. Sorry, these math. My math degree was like decades ago, so I don't always remember all the names of things. But you can describe each move as kind of like a sword or a swap something circuit or something or another. I have to Google this later maybe to kind of be more articulate about it. But there's also like and in those things you could there are ways that you could kind of prove that certain permutation can just never get you to another certain permutation. But oh yeah, inversion number is also related to that for sure. I think I actually talked about it in like something last week or something, or maybe 2 weeks ago. But yeah, I think that. But I think so. That's ahead of. I didn't want to get into all that because I think that requires a lot of kind of math and knowledge that. Well, I mean, it's great if you know it. Don't get me wrong. Like, and as a problem solver, like these are the tools. You always build up your tools so that you keep on knowing and learning more about it. And I think actually group theory and all, permutation theory and all that stuff is actually super interesting. But I also try to solve, at least for now, try to answer the problem in a way that is kind of just general, or not maybe general is not the right word, but like in a way that at least solves the problem without hopefully knowing the least as possible. But yeah, I mean, I think actually, but yeah, I think everything we described so far is just me, just with what I would say, like, what do they call in Kickstarter, like stretch goals or whatever. Like everything I said is stretch code. You actually don't need to know all of it. Like that, we could actually just assume that. Let's roll back some of the assumptions or some of the things that we kind of talked about, which is that let's just start from the beginning where we're like, okay, 6 factorial. Do we know how to get to 6 factorial? Well, there's only six things, and you can assume that and there's only 6 factorial ways to order them. So there's 720 states, right? And on each state, you could do a move that's called a swap that gets you to another state, right? And if you kind of iteratively think about it that way, then and use it a breadth first search, then this is just a graph problem, right? And a graph problem, in a general graph problem, the shortest path, if you exhausted all possible moves or like all possible shortest moves, and some of this is well, a lot of this is actually greedy, and you could prove the greedy in the shortest path in an unweighted graph and stuff like that. I mean, because it stops being greedy when there's negative weights, but we don't have to get into it. That's like algorithm class again. But yeah, but once you exhaust all possible moves, all the states that you cannot get to, then you just can't get to, right? And that's like by default. Uh, yeah, then it's -1. So you can actually. So I'm gonna try this. So I know that we talked about higher power, like more fun, you know, nerdy in a good way. I'm a nerd. Nerdy kind of solutions, but we could actually just solve the base of what they ask you for, which is, well, given this board, do a breadth first search and see if we can get to the end state. And I think that should be sufficient. And that actually doesn't require any of the math. I think some of the state analysis is just to kind of see, figure out the upper bounds on things so that we can kind of figure out if it's worth doing, right? So okay, so I'm going to do that. Yeah. Also, you have, but I do geek out. I do appreciate you could tell that I really geek out on kind of knowing all this math, and you guys are actually way ahead of me in a few things. So I'm happy to kind of be with peers. But cool. Okay. So, and I'm just right now. I'm just going to implement the breadth first search. I don't. I think some of and actually, yeah. I mean, all the things that we talk about, I think is not necessary for the implementation, but it's just more like, okay, so these are the cool things that allow us to kind of bound the problem. Like we started this big problem. It's like, oh, okay, actually, there's a smaller problem, and I mean, it turns out that the way to solve both of them are the same, but these techniques are things that we have at our disposal. That maybe in the future, if maybe if the problem is instead of a 2x3 board, is a 4x4 board, which I think actually is a common game called 15. It's either called 15 or 16. I always forget. Then maybe, excuse me, maybe some of these things are more handy. But yeah, man, and with math, there's a lot of Wikipedia wormhole type things that you can get into and just keep on clicking to learn things. So it's great. Anyway, okay. I think we talked for 15 minutes before I even type a line of code, but even though we roughly know the answer, but I think it's worth it. I'm having fun, so thanks for uh, exploring this with me. But okay, I think in this we'll just have an encode state. So given a board, actually even lazier. I'm just gonna define this as a six-digit base 6 number. Yeah, because I'm lazy. So I mean, you can actually, because I say that I'm lazy in that sense is because if you do 6, because what that means is that you're actually using 6 to the 6, which is actually 46,000 numbers. So that's how you encode it to be cached or whatever, or memorized or whatever it is you're doing. And maybe in other cases it comes into play, but as we talked about, this is actually 6 factorial, so you can actually encode it in I forget what they call it. I think it's just either permutation number or permutation ordering or something like that. I forget what the exact vocabulary is, but you can actually encode it that way in the entire board because there's a 1-to-1 correspondence. You encode the entire board from the board representation to a number from 0 to I guess 719 inclusive. But I'm lazy, so I'm just going to do it to a 6-digit base 6 number, which is 6 to the 6, and it's 46K. But we're not allocating away. We're going to end up using like a hash table type thing. So it doesn't affect the performance other than, I don't know, you get a little annoyed by minor inefficiencies. I just want to point that out. But okay, what am I doing? Okay. Okay. Also, I'm thinking, yeah, okay, I'll just do it. Yeah, did I say that? 4 to 6 is 46,000, yeah. I mean, it's fine because we don't, yeah. I don't know, okay. So that's my encode and LD code. This might actually not be necessary, maybe, but actually. How do we decode? Oh. By hard coded actually. So hold on a minute. Okay. Is it 2 by 3? Oh, I didn't write it either side. Okay. And just to test something. What? How did I get locked out? Maybe because I was talking too much. Hang on. How does it lock out during a session? Am I really talking too much? Okay. Or maybe my internet's slow. Ah, oops. What did he call? Oh, I don't return. I guess that's sad. Yeah. But yeah, so, oh yeah, I probably actually handwave this part a little bit. So I'm actually, the reason why I'm converting these to numbers and boards is that when we do the BFS, it's easier to refer them by states. I mean, I think, so like, just having a number represent a state is a little bit easier than, also this is reworded, so I need to go the other way. But I'll fix that. But, oh yeah, yeah. What was I gonna say? Oh yeah, but it's just generally more efficient if we encode it and then decode it as a number because then you could do, you could pass that around easier versus like having to allocate memory for a two-dimensional array every time, or and that actually takes way more time. So that's why I'm doing this encoding thing. Oops. No. Okay. I have to do this backwards. Uh, Yeah, I'm thinking of insert. Also, I'm just being lazy. I probably could have done this a little bit cleaner. Whoops. Did I not print? Oh yeah, I deleted the printing ports. I don't know why I type it like this. Okay. Because ideally, and you know, if you're correct, if you encode and then you decode your encode, it's the same. Okay, cool. I can just put it here. Now default case is make 1, and if and go is equal to self.encode because well, actually I could just copy and paste this. As a pop. Let's print this just in case. Okay. And now we go, and that's just general breadth for search stuff. And now we just have to make sure we get the states bit. Okay. Yeah, that's we're doing the code. Actually, maybe we just give it a hash. Let's see. Yeah, it should be right. Hopefully. And that's, I think, all you need other than this one, which we have to do. Oh man, I just realized I've been using the wrong inconsistent casing. Well, we'll have to fix that another time. And I think actually we can even be smarter about the swapping or something. But I'm just going to type it out because we could optimize it later. Okay, so I have to figure out where the 0 is. So yeah, there are only 2 or 3 states in each of these transitions in each of these, right? Because the 0 can only go up and left and right. So should be okay. I don't know if I'm doing this clean as possible, but just gonna focus on getting this working for now. Can we do this mathematically slightly cleaner? Is it worth doing it? Maybe it is actually. Then because there's a lot of creating boards otherwise. But basically, I'm going to try to do this manually a little bit. Well, like by thinking, the technology, ultimate technology thinking. Okay, so let's say we want to go up. What's that equivalent to in terms of mathematically, right? I forget which numbers this way goes, but going up means well, let's actually change this array into actually. Well, let me rewrite some part of this code. I think we can actually flatten these to. I think if I flatten these, it'll be cleaner to kind of understand what I'm about to do next. Yeah. How do I? Oh, yeah. I think that's probably way to do it. But, okay, so now that we have a flattened board, now to make this part easier, I guess. Oops. That's what we should be not lying about. Whatever. Six. Mm-hmm. Oh, I have two ways. Oh, 2D array. Okay, so I think this is right. Okay, so now that we find everything, what does going up mean, right? Going up means the number that's or the digit that's 3 pi. Oh, I guess I have to get precision on this. I think also to remember. That's probably a fine thing in 500. Text. I don't know why I'm reindenting the wheels. Well, I was doing something more complicated, I guess. More like that, maybe? Is that it? Nope. Close. Okay, so that's what 0, 1, 2, 3, 4. Okay, so now going up means the index that's 3 less than it. So index plus 3. Now we swap. No, just also just try to think about how to represent that in a clean-ish way, but probably okay. There's no swap function. I need to learn how to learn Python. Okay, I'll just print it out. Okay, and then the left is similarly. Yeah, actually, we could. Now that we generalize it, actually, we could probably do directions in a thing. So directions you go in a way. So going up is -3. Going down is +3. Yeah. And then left, right is just something like that, right? So now we can generalize that by also now we have to add these and position is that and well, I guess just less than 6 since we're hard coding some, though it's not the clean way to do it per se. Okay. Oh, I forgot to implement the swap. That's fair. Uh, I check these. Oh. I guess I phrased it weird. So it does stuff. But we do not check for end goal, that's why. I think I should probably terminate that actually earlier, but let's just see if that works. Yep. Alright, let's try a couple more. And not 14. Well, being wrong is kind of sad. But that's probably not my ones. What am I printing? Oh no, that's just input. That's interesting. That means that means one of our moves is probably wrong. But, huh. Is my math wrong? -3. Plus 3. Sure all my cases are right. But, Is this going to print too much stuff? It might print too much stuff, but let's just see it anyway. That sounds reasonable. So just 2 labs. Am I missing something obvious? I don't know how to look through this debugging thing, so am I moving the non-zero by accident? Shouldn't be, we only move relative to position. This should reword stuff. I mean, I don't think we do anything stateful. Well, Oh, I did a stupid. Um, okay. I got lazy on finding this. So because of this, if you're in the fourth, I allow swap between these two elements. The zero index second element, or the third element and the fourth element. Let's say it that way. Okay. Oops. That's what happens when you take shortcuts, I guess. Okay. Mm, I guess I was hoping that this would symbol things down, but instead it did not. So, okay. Such a hack. Wow, now it's slower. Oh, yeah, okay. Because I don't check that. Okay, fine. Yeah. I was just lazy. This is what happens. I could represent this screen a bit. Ironically, I wrote this so that I could write less code, but instead I might as well have just coded it up instead of this very confusing mess. But okay, at least it's right now. What's my print statement so I can get rid of it? Let's test it one more time. Okay, cool. Yeah, I mean, there's some issues with coding, but I think in general, we went through all that we can with this problem. I mean, at the end of the day, it's a breadth first search problem with some trickiness, and we end up spending about, I mean, like 40 minutes, but we spent like a good 15 minutes just talking about it, so I don't feel that bad about it. Um, cool. Yeah, in terms of complexion, complexity. I think this, yeah. So as I mentioned before, this is but for search, but the state is actually n factorial. But there's only six. Where n is always six, so it only goes up to 720 states in the worst case. So that's how you kind of justify the complexity. Uh, and space is similar because we're using a queue that visits every state. And also like a dictionary to kind of keep the lowest we've seen before. Um, yeah, in terms of an interviewee, I mean, this is kind of straightforward, but I think some of it is just like, well, it's straightforward, assuming that you know how to represent, um, or like if you have the insight that the maximal say is not that much. I mean, I didn't even do things that efficiently, but you could you could certainly do that. Um, Uh, in terms of yeah, I mean it's an okay part. I think it's a reasonably sized both in terms of difficulty and length of a problem for an interview. I think there's a lot of places where you can show off some of the modularity of the code. There's enough code for it to do that. I think like probably I would clean up like this chunk a little bit to modularize it into like like some of this is set up for it to be a graph problem. I could certainly put this into a graph, BFS function or something like that. This is clearly a little bit messy that and some of that I did as a shortcut for typing, even though it didn't work out that way. So maybe by go back. I would have cleaned this up a little bit and changed some of the language, or at least uh, uh, labeled it with additional comments. So I think this is meaty enough to kind of have enough code for it to be interesting to as a critique for like a pseudocode review. As an interviewer, so I think I actually like this problem for all these reasons, and it's not too difficult. In I mean, at the end of the day, it's a breadth first search that's a little bit brute force in that it looks at everything. So I think if you give a hint the right way, I could see a candidate easily spend the rest of his or her time implementing this, and hopefully we could discuss about like, and it's a reasonable enough problem that we could discuss afterwards how you do testing, how you do debugging, and how do you deploy to production, and what are some changes that you make, what are some optimization that you make, and kind of things that we talk about in chat early on before you even dig into the problem. But yeah, otherwise, no, I mean, I think it's a good problem for that interviewee reason. It's a little bit easy on the problem solving part, I think, because it is. But I think that's fine in terms of like if I'm to kind of like to give them kind of an interview based on how they implement and write code. I think this is a good example that I can use for that. Okay, cool. I'm gonna call it a night. It's Wednesday, but definitely I'm gonna be back on Sunday. Tune in, and thanks for checking in. Thanks now to no, I mean you had most of it. I think but yeah, thanks for tuning in now too, and Johnny. But I think I don't know. I think you were definitely got it on your own. I think it's just some of it's just. I think one thing that when you practice a lot, you see is kind of figure out what the basically like the ceiling of how much energy, how much like the maximal complexity is, right? Like, and the way I do it, I mean, it's like a mental checklist that I don't know, just from like doing a lot, right? It's kind of like, okay, can I do this? And like, what is the stupidest, most naive way that I could solve this problem, right? And I think in this one, my first instinct is like, oh, what is the stupidest way I can do it? Well, let's just try every possibility, and it's slightly optimized. Maybe it's not the stupidest way. You're not literally doing like, recursion that's on every possible state, but but yeah, but you look at it and you're like, oh, what, like the number of all, like the entire world of possibilities is only 6 factorial, right? And in that case, you do the math, you bring out a calculator, 720 states. I know we talk about eliminating half, but that's not even that necessary. But yeah, yeah. I mean, I think some of it is practice and just kind of walking down the list. And when you've done enough of these sort of problems, you can kind of get it. Actually, I think that actually reminds me a little bit about like the variation on if it's 16 or 4 by 4, which is 16 or 15, depending on the name of the game you call it. I think I, I I think like so because I think we don't. I don't know if we have to talk about it, but I don't know if this is another problem they might have solved. So maybe this is a spoiler thing. But if it's a 16, I think like obviously in that case, 16 factorial is too far away. But actually, what you can do is I think I had to figure out how like what's the farthest states that you can get. But I think you can actually just do something that meets in the middle, which is another technique that we didn't need to use here. But it'll be interesting to kind of explore to see if I might have to think about it a little bit to see like how big the trees get. But the idea is that you do when I say meet in the middle, you actually do two parallel breadth first search, which like a shortest path is kind of what it sounds like, where like if instead of me exploring all the paths to get to you, it'll be you. It'll be us doing it together in parallel. I think breadth first search to kind of see like, well, where the states intersect, and when they intersect, then that's where we meet, and then you just get the distance from the both sides of it. So if you could imagine like a tree that grows exponentially as the number of steps go on, and And you could think about it just like, you know, mirror it so that like the top and then so that it intersects in a much smaller way so that like it goes through like a I guess like a diamond shaped type thing. Oh yeah, I'll definitely check out that link later. I think that's how I would think about it. Maybe it's a problem. Maybe it's a Leetcode problem, and I'll get this out of it, and then I could explore those